One of the methods is the manual method for determining erythrocytes in the Galiaev chamber. The Galiaev chamber consists of thick glass in two parts, the upper and lower, which are engraved in the grid of the Galiaev chamber. Grids, grids, grids. In the device, which we will discuss at a later time. To count the electrocenters in this chamber, we need to carefully cover the grid with a cover slip until the so-called rainbow or Newton's rings appear, after tightly rubbing the grid with smooth movements and forming rainbow rings at its edges. We will then need to fill this chamber, both the lower and upper parts if necessary, with a 2 kHz, 3% saline solution. The grid of the Galiaev chamber contains approximately 225 large squares. There are approximately 15 large squares horizontally and 15 vertically. 225 squares. The large square in the Galiaev chamber is such a square, divided into 16 small ones. It contains both small squares and large squares, divided by various horizontal and vertical lines, as well as numerous shaded large squares, all distinct in their arrangement. The volume of a small square at the heart of Galiaev's design is 1.4 m. Let's begin. 1, 2, 3. We are in the process of providing precise and accurate measurements in microlighters, ensuring that every detail is meticulously accounted for in our scientific procedures. Therefore, essentially, in order to calculate the square units, which we will basically consider as square counts, we need to multiply these microlighters by 4,000. Let's return to the definition of microlighters. We take the stone root and will explode it, as I have already shown, with a volume of blood that will contain erythrocytes. This blood, we dilute it 200 times. For this, we take 4 ml of 3% sodium chloride in a test tube, and here we introduce 20 microliters of a T-rose suspension of erythrocytes using a micropipette. And it is this suspension that we need to fill the cone with. For this, we perform the introduction of this suspension. And under the cover slip, we very carefully introduce a drop of this suspension from one side and from the other. And therefore, to level the error, we count the square diagonally, divided into 16 small ones. We can place in the left and upper corner and also count 5 squares diagonally, divided into 16 small ones. In this case, we sequentially count the first square of those retrocenters, which will appear as black dots, located inside the small square, as well as along the left or upper line, without counting the red blood cell lying on the bottom or right line, since their counting will be done in the subsequent counting of the following small squares. Examples of the latest counts of red blood cells located in the first large square. We can list the first principles, examples of counting. Subsequently, we move on to another large square. The town is noted as small, and this makes sense according to the reform of the large square located in this square. And there, in the next strip, it equals 4 squares, and another 3 squares. That makes sense. Let's continue. We will diverge, and we record all the obtained details, after which we are at the forehead of this square. It is located. It adds up. In this case, we obtain 235 samples across all 5 squares. Now we need to perform a recount. At the beginning, it per microliter. For this, I write down the formula, and the content of the electroactive substance in 1 microliter is A, meaning this is the amount of electroactive substance you counted in the 5 squares. We must multiply by the type of blood. We divided it by 5 times, by 3 times for 5 squares. Divide by the number of small squares. There will be 85 large squares, as each has 16. And also to bring the value to 1 microliter, considering that the volume of 1 small square, for example, means that 1,000th of a microliter will have a volume greater than 2,500. As a result of reducing these coefficients, we will get the formula A multiplied by 9.3. Let's substitute our value A 9.3 multiplied by 9.3, we got 2.3 multiplied by 10.6 per microliter in this case. Sutwenzel 30, X can be 10, 6 per microliter. Yes, 10, 6 per microliter. Compared to the norm, our value turned out to be